Welcome to the video for Chapter 24. Today we're going to be talking about what happens when a transmission line has something attached to the end of it. After all, if we don't attach anything to the transmission line, then what's the point of it? So we need to understand what's going to be the impact of having something connected to the end of it. And the answer is it can be pretty complicated. We can find that there'll be some cases where it's going to be reflection. There'll be other cases where there'll be no reflection. And it's really going to depend upon the characteristics of the line and the characteristics of the load that is attached to it. So we're going to talk a little bit about characteristic impedance. Remember that we talked about characteristic impedance of free space. We found that that was 377 ohms. We found that there can be different characteristic impedances of different materials as electromagnetic waves are propagating through it. The same is going to be true of transmission lines, that we will find that there are different amounts of characteristic impedance for each of these lines. We're also going to talk about what happens at the end of the line. So in other words, will there be reflections? And if so, how strong will those reflections be? And what will be the impact of those reflections? And we're going to find that there is a new quantity called the voltage standing wave ratio, which is going to be a measure of how good the line is, or rather how good the match is between the line and the load that's attached to it. Our historical perspective today is another person who's still alive, James West. You may never have heard of him, but he co-invented the foil electret microphone in 1962. 90% of the microphones that you use today are based on this invention. He was a very active inventor. He worked at Bell Labs for 40 years, and he has more than 40 US patents. So let's talk a little bit about what happens if we send a sinusoidal wave down a transmission line. You'll remember from the previous chapter that we talked about how a transmission line has a capacitance per unit meter. We're going to call that C hat, and the inductance per unit meter, we're going to call that L hat, and how C hat and L hat are essential characteristics of the line, and how we can determine different important things about the line based on L hat and C hat. One of those things we can measure is the velocity of propagation. We found that any wave will propagate down the transmission line with that characteristic velocity, and it's not just sinusoidal waves. We tend to think that waves are all sinusoidal, but it could be a square wave, it could be a triangular wave, it could be an arbitrary wave of any shape. But sinusoidal waves are our favorites because everything else can be made of sinusoidal waves, and because it's very easy for us to generate sinusoidal waves. And as we're going to see in a future lesson, sinusoidal waves are very, very good at creating electromagnetic radiation, so antennas in other words. So let's really focus on our favorite waves. Any wave will work, but we're going to focus on our favorites, which are sinusoidal. So we're going to say that we're going to focus again, and I think you're going to find that this analysis is going to be very similar to the one that we did for electromagnetic waves in free space or dielectric. We're going to focus on a time harmonic sinusoidal wave. So we're going to take the time dependence of the wave and we're going to separate it out from the spatial dependence. We're going to say that the time dependence is going to be e to the j omega t, which is really equivalent to saying that it's a cosine of omega t. We aren't yet specifying what the spatial variation is going to be. We're just going to call that the most generic thing we can, which is v of z. So we've separated out the time dependence and the spatial dependence. The question is, what is the spatial dependence going to be? And can we figure out what that spatial dependence is? Spoiler alert, yes we can. And second spoiler alert, it's going to also be sinusoidal. So we're going to find that if it is time harmonic, then it must also be spatially harmonic as well. So let's go back to our wave equation from the previous chapter, equation 23.16. We remember that we derived the telegrapher's equations, or we call them transmission line equations. We derived those directly from the equivalent circuit model and Kirchhoff's laws. From there, we derived this equation, which told us that waves would propagate down a transmission line. Now we're going to substitute our new equation, 24.1, into the two places where v of z comma t occurs in this wave equation. So you can see all I've really done there, I took away the real part, and we'll take the real part at the end. All I really did was to substitute our new separated version for v of z comma t. Now we can look at the left side of this. It's a second derivative with respect to space. Well, the second derivative with respect to space is going to have no impact on the e to the j omega t, so we can just pull that out. We don't yet know what v of z is, so I can't evaluate what the second derivative of v of z is with respect to z, but I do know that it will be there, and that's really the entire z dependence is contained within v of z. And then on the second term, I know that the v of z term is unaffected by the derivative with respect to time, so that's going to come out and be separated because that second derivative with respect to time has no impact on v of z. So I'm going to take that out. When I do the second derivative with respect to time of e to the j omega t, I pick up 2 copies of j omega. The first derivative gives me a j omega from the chain rule, and then the second derivative gives me another j omega from a second application of the chain rule. So it becomes j omega, the quantity squared. Don't forget that there was already a negative L hat C hat, so I'm going to keep the negative L hat C hat, and then the e to the j omega t just sticks onto the end there. We're going to cancel the e to the j omega t's because they're in both of the terms, so we can cancel those out. And then j squared is equal to -1. That -1 times the negative sign is going to give me this positive sign right here. So this is negative j squared, which becomes a positive sign. The L hat and C hat stick around, the omega squared sticks around, everything else is going to stay here. So that equation is actually in exactly the same form as the one-dimensional Helmholtz equation, which is going to have k squared in place of that constant L hat C hat omega squared. We know that this is a very well-known differential equation. We know the solutions to this equation, but just for the moment I just want to remind you that k, we replaced k squared in for L hat C hat omega squared, so k must be equal to omega times the square root of L hat C hat. And we know that the velocity is equal to 1 over the square root of L hat C hat. So this k is equal to omega divided by v. And that's exactly the same thing that we found when we were talking about electromagnetic waves in free space. We called it omega over c at the time, but now it's omega over v. And so it's reassuring here that we're sort of closing a loop, and we're seeing that as we're doing this derivation for transmission lines, we're getting essentially the same exact things that we got when we were doing this derivation in free space. So as I mentioned, we know the solution to the Helmholtz equation, and it is a general form that has a right moving wave or a positive moving wave. This one is moving in the positive direction, and then there's a negative moving wave, and that one's moving in the negative direction. So that's a sinusoidal wave in free space. E to the jkz, or e to the negative jkz, is going to be sinusoidal in space with a component moving to the right and a component moving to the left. So, just as we saw in free space, if we assume that the signal or that the wave is varying sinusoidally in time, then the math requires that it also vary sinusoidally in space. And not only that, but the rate at which it varies sinusoidally in space, which is this constant k, that k is going to be specified by the rate at which it changes in time divided by the velocity of propagation. So we're going to find that that there is a wave that's moving sinusoidally in time and sinusoidally in space, and the relationship between those two is going to be related by equation 24.6. Try not to belabor this because we talked a lot about that when we first saw it in free space, but it's just as important here as it was then. Just wanted to mention that if you did the same analysis for the current, you would also again separate the time component of the current into an e to the j omega t. You'd have a spatial component I of z. You would, if you did the exact same derivation, you would yield a corresponding differential equation, and you would end up with the constants, and here I just named them different letters, c e to the minus jkz and d e to the positive jkz. And so we'll find that the same derivation, we would be able to find the same quantity for I as we did for z, just with perhaps different, certainly not perhaps, but certainly with different constants. So if we combine together the z and the t component again, we're going to get our old friend, the equation for a traveling wave. Sorry, I couldn't remember the word traveling there for a second. So we have a traveling wave with one component moving in the positive direction and one component moving in the negative direction. Now for the moment, for the rest of this section, let's just think about the positive moving component. So we're going to ignore the negative moving component for right now. We can do this if we think, oh, that wave is going to be generated at negative infinity. So I'm over here at negative infinity, and I've got something that's creating a wave, and it's sending it down the line here. I'm going to assume that it has never encountered any sort of obstacle, and so nothing has ever reflected back. So it's just constantly moving to the right, and nothing else is happening. So the question is, as that wave is moving to the right, what sort of important analysis can we do? Well, what we would really like to be able to do is find out what is the current associated with that voltage. So notice that here, all I've done here is in equation 24.11, I have taken my solution from 24.7. I've said, nope, I'm not going to have a negative moving wave. I'm only going to have the positive moving wave. And you know what? Just to make things simpler, I'm going to rename this V sub 0. That's really all that I did to go from equation 24.7 to equation 24.11. Now the question is, what is the current that's associated with that wave? So we know that the current is going to have to be at the same frequency, both in space and time. We know that it's going to have to be in phase, but we know that it could have a different amplitude. And in fact, it definitely will have a different amplitude. So the question is, what is the relationship between V sub 0 and I sub 0? So we're going to substitute these two expressions into either of the two transmission line equations from the previous chapter. We're going to use the second one here. We could have just as easily used the first one, and we would obtain the same exact result. So just reminding you, equation 23.13, an equation from the previous chapter, the second of the two transmission line equations. All I'm going to do is I'm going to take the partial derivative of v with respect to z, and I'm going to plug in my new equation for the positive moving wave of v. And then over here on the right-hand side, I need the partial derivative of I with respect to t, and I'm going to plug in my equation for the positive moving current. And when I do that, I can now take the spatial derivative with respect to z. Notice that that spatial derivative, I'm going to, by the chain rule, there's a j times negative k. And so that's where I get this negative jk over here. I have the negative L hat, which was part of the original transmission line equation. And then over here, I have a j times omega, which is the factor that multiplies t. So the derivative of that is going to pick up an extra j omega right here. So when I solve this equation, I can cancel, well, I guess I won't cancel. I'll just say I'm going to cancel out the e to the j omega t components, but for now I'm going to leave the e to the j negative kz component, because k times v of z, so I'm going to cancel out the negative sign, and I'm going to cancel out the j. So I'm left with only k times v of z on the left, and on the right, I have omega times L hat times I of z. If I solve that equation for I of z, it's k over omega L hat times v of z. And then if I were to define the characteristic impedance of the transmission line as the voltage divided by the current. When we did it in free space, it was the electric field divided by the magnetic field, but now we're going to use our friend Ohm's law to say, oh, V equals I times R, or V equals I times Z, so therefore Z equals V divided by I. So if I take this equation and I rearrange it to find V divided by I get omega times L hat divided by K. But I know that, if I go back up to equation 24.6, which is way up here, 24.6 gave me a relationship between K, omega, L hat, and C hat. So I'm going to come back down here. K is equal to omega times the square root of L hat times C hat. So this is equal to omega times the square root of L hat times C hat. Well, those omegas are going to cancel. Half of the L's are going to cancel, so that's going to leave me a square root of L hat in the numerator, and it becomes the square root of L hat over C hat. So we just did 4 pages of work to get one equation. This equation is super, super important to us, though. So if everything that we did up until now, you were like, oh, I think I understood it, I'm sort of hanging on by my fingernails, yeah, I get what you're doing, there's no way I could have done this on my own, that's normal. That's the way that I felt when I was a student. That's the way I felt the first time I taught this class. So just be confident that if you followed along well enough to have confidence in this result, most of the work that we're going to do for the rest of this is going to be applying this result. So we know that if the voltage along the transmission line is time harmonic, that was our initial assumption, then it will also vary sinusoidally in space. If it is time harmonic, then it must also be spatially harmonic. Furthermore, the current will vary in precisely the same manner, with the same velocity and with the same speed. The same velocity and the same phase. This should say the ratio between the magnitude of the voltage and that of the current will be constant and can be easily calculated as the square root of L hat over C hat. Now, we had some results from the previous lesson that I wanted to bring to your attention. We were able to calculate L hat and C hat for each of three types of transmission lines. You know, we have a coaxial cable, so that's where we have two conductors that are coaxial to each other. The microstrip line, that's where there's, oh boy, this is hard. That's where this, you know what? You all know what a microstrip line looks like. Okay, maybe out here it works a little bit better. They're sort of vertically separated from each other, and then the twin lead is two conductors that are side by side. So we've seen the three types of transmission lines. I'm just going to get rid of that so it goes back into place. We've seen the three types of transmission lines. I just wanted to draw to your attention the fact that if you plugged in the quantities that we had for L hat and C hat in the previous lesson, they were in a table in the previous chapter, you end up with 1 over the square root of mu times epsilon for all three of these cases. Now, remember that mu is mu sub 0 times mu sub r. I'm sorry, mu is mu sub 0 times mu sub r. Epsilon is epsilon 0 times epsilon r. So this is sort of just a shorthand notation that includes both the free space quantity multiplied by the relative quantity. Now, furthermore, if we plugged in the quantities that we had for L hat and C hat into this equation up here, into this equation, which is our big master equation from the first 4 pages, if we did that, we would find these equations for the characteristic impedance of each of the three types of transmission lines. Now, you could calculate L hat and C hat and then plug them into equation 24.18. You could do that, no problem, and if you needed L hat and C hat for some other purpose, you could certainly do that. But if you don't need L hat and C hat for any other purpose, now you've got these three equations here, which you can use to calculate the characteristic impedance in a single step. I just also wanted to draw your attention to the fact that, remember, the square root of mu sub 0 over epsilon 0 is 300, oops, that's poorly written, 377. Because that was the characteristic impedance of free space. So when we're calculating these quantities, we can use that 377 as a little shortcut, and I'll show you that in a couple of the examples. Another thing I wanted to draw your attention to is that 1 over the square root of mu. Let me try that again. 1 over the square root of mu times epsilon is equal to 1 over the square root of mu sub 0, mu sub r, epsilon 0, epsilon r. But mu sub r is almost always going to be equal to 1. And therefore, this is going to be 1 over the square root of epsilon r times 1 over the square root of mu sub 0, epsilon 0, and that is equal to c. So this is a real nice shortcut version of the equation to calculate the velocity. You don't need to calculate L hat and C hat. You don't even need to do 1 over the square root of mu times epsilon. It's just c divided by the square root of the relative dielectric constant. And we're going to use that a lot. Okay, so let's determine the propagation velocity and characteristic impedance of a coaxial cable with an inner radius of 0.5 centimeter, an outer radius of 1 centimeter, and a relative dielectric constant of 10. So velocity is the easiest. It's c divided by the square root of epsilon r, which is 3 times 10 to the 8th, divided by the square root of 10, which is 9.49 times 10 to the 7th meters per second. So as fast as that, we were able to calculate the velocity. The characteristic impedance, now again, if you had L hat and C hat, plug them into the equation that we have. But in our case, we don't have that. So I'm gonna do the equation from that table. It's the natural log of b divided by a divided by 2 pi. Let me just double check that I got that right. Natural log of b divided by a over 2 pi. Good. Now this is going to be equal to, I'm just going to take one extra step here and say this is mu sub 0 over epsilon 0, and that's mu sub r over epsilon r, times the natural log of b over a divided by 2 pi. Now we know that this quantity is 377 ohms, and we know that that quantity is 1. If we don't specifically tell you that it's a ferromagnetic material, you can always assume that mu sub r is equal to 1. So this then is equal to 377 divided by the square root of epsilon r, which is the square root of 10. And there we avoided having to do 1.566 times 10 to the negative 6th, 8.854 times 10 to the negative 12th, because even professors don't like typing that into their calculator. And then we have natural log of b divided by a. B is the outer radius, so that's going to be 1 centimeter divided by 0.5 centimeters. And I didn't need to convert those into meters because the units are going to cancel out. And that's divided by 2 pi, and that's going to give me 13.1 ohms. So does that mean that this transmission line ever at any place has a thing where you could measure it with an ohm meter and see 13.1 ohms? No. It just means that the ratio of the voltage to the current as a particular signal is flowing down it, actually any signal, as any signal is flowing down it, that characteristic impedance is going to be 13.1 ohms. Determine the propagation velocity and characteristic impedance of a twin lead transmission line in which each wire has a radius of 0.1 millimeters and the distance between the wires is 2 millimeters and the material between them has a relative dielectric constant of 5. Okay, now in this case, just wanted to draw your attention to the fact that I am a trickster. This quantity is d, but remember that I told you that a represents the diameter, so a is equal to 0.2 millimeters. And so if you got to watch that word radius here. In this case, it says radius, so you got to multiply it by 2. So the velocity is c divided by the square root of epsilon r, which is 3 times 10 to the 8th divided by the square root of 5, which is 1.34 times 10 to the 8th meters per second. And then z sub c, you look it up in the table for the twin lead, that's going to be the square root of mu over epsilon times the inverse hyperbolic cosine of 2 millimeters divided by 0.2 millimeters divided by pi. So this is 377 divided by the square root of 5. And then I did the inverse hyperbolic cosine on my calculator. I got 2.993 divided by pi, and I got 161 ohms. So we can now pretty quickly and pretty easily calculate velocity and characteristic impedance for any transmission line if we're given the physical characteristics of the line. But the title of today's chapter talks about reflections, terminations and reflections in particular. So let's talk about what happens when there is a wave that is reflected. So remember that in the previous section, we really just talked about the positive moving wave. But in general, there will also be a negative moving wave as well, because every transmission line must end. And when that happens, the signal can be reflected back from the termination, and it's going to begin to move in the opposite direction. We've already seen an equation for the voltage of a positive and negative moving wave. So this is the positive moving wave, and this is the negative moving wave. You could also think of this as the incident voltage, and this is the reflected voltage. Now, we don't really do the transmitted voltage like we did with the dielectric materials. We just have incident and reflected. We know that the magnitude of the positive moving current is 1 over z sub c, as large as the positive moving voltage. So we can take whatever the voltage was whatever the amplitude was of the voltage, we can multiply that by 1 over z sub c, and that will give us the amplitude of the current. But there is one little detail, and that is this negative sign right here. I just want to draw your attention to the fact that must have a negative sign there. Let me show you where that negative sign comes from. I'm going to scroll back up here to this derivation that we did, and I decided not to rederive it because I thought that it was going to just be too much of a hassle for you and for me. So just notice here that in equation 24.13, if this were a negative moving wave, then this would be a positive sign right here instead of a negative sign. And if that had happened, then this would have been a positive sign instead of a negative sign. And if that had happened, then there would have been an extra negative sign right here. And if that had happened, we would have found that the characteristic impedance, gosh, there's a lot of marks on here, the characteristic impedance would have picked up a negative sign there, which would have been a negative sign here, but only in the case of the negative moving wave. So all of that is just to show you where that negative sign comes from, because I haven't ever seen a textbook that does a good job of explaining where that negative sign comes from, and it took me a while to figure out where it came from. So I just wanted to make it so you don't have to take that extra time to do that. Okay, so we know that 3 of the 4 terms are going to be positive, that the incident wave voltage is positive, the reflected wave voltage is positive, the incident wave current is positive, and but the reflected wave current is going to be negative. So we can see what's going to happen if we have a transmission line that has a characteristic impedance of Z sub C, and it's terminated in a load Z sub L. Now we're gonna have to keep straight our capital Z's and our lowercase z's. It's just an unfortunate thing here that capital Z represents impedance and lowercase z represents spatial variation. So we know that we can choose Z equals 0 to be at any point, and we're going to choose it to be right here. We're going to choose it right at the termination, which means that everything over here is Z is less than 0. If it went over here, which it won't, that would be Z is greater than 0, but nothing happens over there. There's no line over there. It's just going to end at the termination, and possibly as it's coming in, part of it is going to reflect back. The question then is how much is going to reflect back. But we've just made an arbitrary choice of Z equals 0 to be at the termination point. If we hadn't made that choice, everything that we're about to see would still be valid. It's just that the math would be a little bit harder. So we know that we're going to take the impedance, capital Z, so this is the impedance of the transmission line, and this is the location along the transmission line. So that impedance actually varies from point to point, and that's kind of a weird thing to get your head around, is that the total impedance of the line is going to vary according to where you are on the line. We're actually going to have an entire tool called the Smith chart, which is going to be designed to help us deal with that complexity. So here all I did was take V of Z from the previous page and I of Z from the previous page. Remember, 3 of the 4 are positive, the 4th one is negative. Don't forget this 1 over Z sub C. That 1 over Z sub C is in the denominator, so it will become a Z sub C in the numerator, but for right now I'm going to leave it as 1 over Z sub C in the denominator. And so we're finding ourselves then, what we want to do is calculate what is the impedance at the load. So I'm going to set Z equal to 0 in each of these 4 terms. And when I do that, then e to the jk0, or e to the negative jk0, is just going to be 1. So this becomes 1, and this becomes 1, and this becomes 1, and this becomes 1. And I know that if that's at the load, then that must be equal to the impedance of the load, because the voltage at the right end of the wire must equal the voltage at the load, and the current leaving the right end of the wire must equal the current entering the load, so they have to be equal to each other. So I can take equation 24.22, I take the Z sub L, I'll move it over to the left-hand side, but everything else is going to stay the same. The 1 over Z sub C is going to move up into the numerator and just become Z sub C, and all the exponents become 1, so I'm left with equation 24.23. Now I'm going to define gamma to be equal to B divided by A. Remember that this is the reflected wave, and this is the incident wave. And so if I take the reflected wave amplitude divided by the incident wave amplitude, that's going to tell me how much of the signal is going to be reflected. And I can rearrange equation 24.23, this equation right here, I can rearrange that to yield equation 24.25, which is our second big result of the day, which says that if you know the load impedance and you know the characteristic impedance of the line, then you can calculate the reflection coefficient. And that will tell you how much of the incident wave or the incoming wave is going to be reflected away from the load. So the proportion of the incoming wave reflected at the termination only depends on the load impedance and the characteristic impedance of the line. It doesn't depend on anything else. And so that's a really important result. I want to remind you that we now kind of have a chain here, and that is that we're going to use the geometry of the transmission line. From that we can find L hat and C hat. From those we can find the velocity, and we can find the characteristic impedance. Now maybe we do have some equations that can skip that intermediate step, but ultimately it comes from that intermediate step. And then from Z sub C, let me draw that arrow so it's coming directly from Z sub C, we can now find the reflection coefficient. So if you, and I also have to have Z sub L, the load impedance. So if you tell me about the geometry of a line and what is attached to the end of it, I can tell you how much of a signal will be reflected when it hits the end, when it hits the termination. So, oh yeah, I said you can derive this boxed equation from equation 24.23, but I don't want you to wonder how that's done. It's really not a mystery. So let's do that one together. Z sub L equals Z sub C times A plus B divided by A minus B. That's our starting point. I'm going to multiply both sides through by A minus B. So I have Z sub L times A minus B equals Z sub C times A plus B. I'm going to say Z sub L, whoops, Z sub L A minus Z sub L B equals Z sub C A plus Z sub C B. And then I'm going to separate out the A components. Z sub L A minus Z sub C A equals Z sub C B plus Z sub L B. And then A times Z sub L minus Z sub C equals B times Z sub L plus Z sub C. And gamma is defined to be B divided by A. So if I take that previous equation, I'm gonna take A, I'm gonna move it over to here. This term I'm gonna move it over to here. That's gonna be Z sub L minus Z sub C over Z sub L plus Z sub C. And that's the quantity that we were given in our boxed equation. So that's how that result was derived. I think that it's worth seeing at one time, and now you'll have complete faith in being able to apply that equation. Speaking of applying that equation, let's determine the reflection coefficient when the transmission line of example 24.1 is terminated in a 100 ohm load. Let me just remind you that the characteristic impedance of that example was 13.1 ohms. And so therefore gamma is equal to Z sub L minus Z sub C over Z sub L plus Z sub C. And that's equal to 100 minus 13.1 over 100 plus 13.1. And that is 0.768. So 77% of the strength of that signal is going to be reflected back from the load. But we're coming from a line that has 13 ohms of impedance, and at the end of it we attached 100 ohms of impedance. That's not a very good match. If those two quantities were equal to each other, then we would have no reflection, as we're going to see in just a little bit. Sorry, spoiler alert. But here we're getting 77% reflection because that's a pretty bad mismatch. So that mismatch is resulting in high reflections. Now, a coaxial cable, and this is interesting because we don't have all the information that I thought we would need here, but we have all the information that we do need. A coaxial cable has a discontinuity in the dielectric constant. So I'll draw the cable here. So the cable has a break, and on the left of that break, epsilon r equals 4, and on the right of that break, epsilon r equals 6. Everything else is going to stay the same. All the inner diameter, the outer diameter, everything else is going to stay the same. Calculate the reflection coefficient. Well, first of all, will there be a reflection? Yes. Anytime that there's a discontinuity of any type, anytime that the two lines are not matched to each other, you will in fact have a reflection. So the reflection coefficient is Z sub L minus Z sub C over Z sub L plus Z sub C. Get ready for a big equation here, because I know that this is mu over epsilon times the natural log of B over A divided by 2 pi, and then that's, oh, and I should clarify, this is mu over epsilon of the second material, because we're treating the second material like the load, and the first material is like the line. So this material over here on the right, that's equivalent to a resistor. It's equivalent to an impedance. We don't know what that impedance is, but we do know that there's a discontinuity here, and that configuration can be treated as though it is a transmission line with a load. So this is Z sub L, and this is Z sub C. And so we know that this is going to be epsilon 2 associated with the load, but then associated with the line is going to be epsilon 1. And that's the natural log of b over a divided by 2 pi. Over here it's mu over epsilon 2, natural log of b divided by a over 2 pi plus the square root of mu over epsilon 1, natural log of b over a divided by 2 pi. And all of the natural logs are going to cancel, which means that the inner and outer radiuses don't matter. Inner and outer radii don't matter because they're constant, so they cancel each other out. The 2 pi's also cancel each other out, which is nice. Assuming that mu1 and mu2 are identical, which they almost certainly are, then those will also cancel. Oh, and I forgot to write that this is epsilon 1. And as a matter of fact, remember that epsilon 2 is equal to epsilon 0 times epsilon r2, and epsilon 1 equals epsilon 0 times epsilon r1. So actually the epsilon 0 components in each of these also cancel. So we're left with 1 over the square root of epsilon r2 minus 1 over the square root of epsilon r1 over 1 over the square root of epsilon r2 plus 1 over the square root of epsilon r1. And that is equal to 1 over the square root of 6 minus 1 over the square root of 4 divided by 1 over the square root of 6 plus 1 over the square root of 4. And when we work that out, it is negative 0.0918 divided by 0.908, and that is negative 0.101. Couple of quick observations. It's a negative reflection coefficient. Don't let that bother you. It can be positive or it can be negative. It just means that the signal will be inverted as it hits the load. The second thing is not very much reflection, only about 10% here. About 10% reflection, but we wouldn't expect very much reflection because not very much changed, right? The inner and outer radii stayed the same. There was a relatively minor change in the relative dielectric constant from 4 to 6. So yeah, I really wouldn't have expected very much change. And in fact, that matches what we found. Now we can express the total voltage and the total current in terms of gamma. Remember that before we had different constants here. But if this is the incident wave, and this is the reflected wave, and down here this is the incident wave, and this is the reflected wave, what we're going to find then is that we can write equations for the total voltage and the total current at any point along the line. Don't forget this negative sign here. That negative sign is important. And this gamma now, the gamma is showing the ratio of the reflected wave amplitude as compared to the incident wave amplitude. So to go from voltage to current, you're going to need the characteristic impedance. But to go from incident to reflected, well, that's going to require that you know gamma. And so we have both z sub c and gamma in these equations. So there are 3 special cases. Special case number 1 is a short circuit. And if there's a short circuit, which is shown here in this picture, a short circuit is literally just a wire, 0 impedance between the terminals. What happens there? Well, if we plug in z sub l equals 0, so here's z sub l equals 0, we end up with negative z sub c divided by positive z sub c, and that gives us a negative 1. So if we have a short-circuited line, we know that gamma is equal to negative 1. And so we can plug that in for gamma. Remember that this is where gamma went. So now it's negative 1. And if we do some complex arithmetic here, it's not complicated, it's just complex, we end up with a quantity negative 2 v sub 0 sine of kz sine of omega t. And this generates what we call a standing wave. And we saw a standing wave before when we talked about an electromagnetic wave that's coming in incident upon a perfect conductor. It's exactly the same thing here. The only thing that I want to draw to your attention here is that this is the termination point, and I just did a terrible job of drawing it, but you know what, let me try a circle. That's the termination point right there. And notice that even though the wave is growing and it's shrinking and it's growing and it's shrinking, it is always equal to 0 at that point. V equals 0. And why is V equal to 0? Because it's short-circuited. And what do we know about a short circuit? We know that in addition to Z sub L being equal to 0, the voltage is also equal to 0. So that voltage equals 0, and that means that if we had gotten anything other than 0 at all times on that far right side of the line, we would have known that we had done something wrong. Now the second special case is an open circuited line. That's where the impedance of the load is infinitely large. Now of course it can't actually be infinitely large. It's just very, very, very large, but it can be, for practical purposes, it can be infinitely large. So if we did that, we can put in infinity for Z sub L. Don't tell your math friends that I said you put in an infinity. Of course, technically, we're taking the limit as Z sub L approaches infinity. And when we do that, then, of course, the Z sub C becomes negligible, and we have infinity divided by infinity. Again, technically, we'd apply L'Hopital's rule, but regardless, we're going to find that it's going to be equal to positive 1. So if we have an open circuit, we get gamma equals positive 1. In both cases, in the case of a short circuit and in the case of an open circuit, we have 100% reflection. It's just that whether it's reflected in the same amplitude or reflected with a negative sign attached to it. So if we put these together, remember that this is where gamma went. So we're going to put gamma right there, and then when we again do a little bit of complex arithmetic, we end up with a cosine of kz times the sine of omega t. And now over here on this point, we don't require that the voltage be equal to 0 because it is in fact an open circuit. If we did this same exact analysis for current though, we would find that the current goes to 0. And the reason for that, of course, is because it's an open circuit. So we know that the current here, I, has to be equal to 0. So we have the two special cases, the open circuit, short circuit and the open circuit. And now we have one more special case, and that is where the load impedance is equal to the characteristic impedance of the line. So if we plug in Z sub C for both occurrences of Z sub L in our equation for reflection coefficient, the numerator all of a sudden is Z sub C minus Z sub C, which is equal to 0. And this is known as impedance matching. So it is impedance matched. Impedance matching is highly desirable because it means that there will be no reflections. And it turns out that reflections are a real pain in the neck. And we'll talk more about impedance matching next time, and we'll talk about why reflections are a pain in the neck next time. But for now, just know that this is the desirable state, that we really want to be in a place where there are no reflections. 100% of the incident signal is absorbed by the load, and nothing is going to be reflected back down the line. So gamma equals 0. That's our sort of our comfort spot. Now we've got three special cases. There's the short circuit, the open circuit, and impedance matched. But in reality, most of the time we won't be in any of those special cases. We'll just have some slightly or possibly significantly mismatched load. And so the question is, what's going to happen in those cases? Well, in those cases, we're going to have an incident wave. So again, we have the incident wave, and we have the reflected wave. Sometimes they're going to be interfering with each other positively. If they're in phase, then they're going to have their amplitudes are going to add together. But if they're out of phase, if they're 180 degrees out of phase, then their amplitudes are going to subtract. And so we're going to find that the maximum voltage is going to occur at 1 plus the magnitude of gamma, and the minimum voltage is going to occur at 1 minus the magnitude of gamma. So when I say magnitude in this case, I actually mean absolute value. So it's 1 plus the absolute value of gamma and 1 minus the absolute value of gamma. And we can define a new quantity, which we're going to call the voltage standing wave ratio, the VSWR. It's always pronounced VSWR. So if you say VSWR, you'll sound like an amateur. You want to say VSWR. So the VSWR is the Vmax divided by the Vmin. And if we just take our two definitions, our two expressions, 24.35 and 24.36, and we plug them into 24.37, then we end up with an expression for the VSWR in terms of the reflection coefficient. So just as a reminder, as I mentioned to you before, we can go from geometry to L hat and C hat, and then L hat and C hat will go to the characteristic impedance, also the velocity. We'll need to know Z sub L. Those two things together will give you gamma, and then from gamma you can find the VSWR. Now if that sounds like a really good multiple part exam question, you're thinking like a professor. So my observation is think about this chain of problems. I might not ask you all parts of it, but I might well ask you several parts of it, and the answers of each might build onto the answers of the next. If you were to rearrange equation 24.38, you could get equation 24.39. Up here, you're given gamma, and you go to the viswar. Down here, you're given viswar, and you can go to gamma. And no, I'm not going to make you derive the second of those from the first one, but it's not hard to derive if you tried to. Notice that viswar equals 1 is the ideal case. If gamma equals 0, so if I had gamma equals 0 here, then the viswar would be equal to 1. And that would be the case for impedance matching. So if the line is impedance matched, then the reflection coefficient will be 0 and the viswar will be 1. Viswar equals 1 is the ideal case. That's the best case scenario. So any viswar that's substantially higher than 1 indicates that the line is poorly matched to the load. Lots of reflections are going to occur. Both open circuited lines and short circuited lines have an infinite viswar. So if let's go back up here and say if gamma is either positive or negative 1, so that's going to be 1, you end up with 1 minus 1 in the denominator, and whatever is in the numerator, that's going to go to infinity. So if a viswar higher than 1 is undesirable, then a viswar of infinity is very, very undesirable. So we just got to bear that in mind as we're working through these problems, that we don't want to open circuit or short circuit our lines. I have a good story about that I'll tell you in class, but for right now, to preserve my own anonymity, I'm going to wait and tell you that one in person. So calculate the viswar for the transmission line discontinuity in example 24.5. Just wanted to remind you that gamma in that case was 0.101, and the viswar then is going to be equal to 1 plus the absolute value of gamma. Was that gamma positive or negative? I can't remember. Let's see here. It was, oh boy, we went way back there, didn't we? Sorry about that. It was negative. I'm glad that I double checked. So it's negative 0.101. And as soon as that finishes drawing, it will skip back down. So gamma was negative 0.101. And this is 1 plus the absolute value of gamma divided by 1 minus the absolute value of gamma, which is 1 plus 0.101 divided by 1 minus 0.101, and that's going to give me a viswar of 1.22. And so again, a viswar of 1 is perfect. 1.22 is not bad at all. But we're not getting very much reflection here, so it is a pretty well-matched situation. We're not surprised that that's the case. Now, you will want to be able to have a real good physical understanding of what the viswar represents. So when I talk about Vmax and Vmin, if those things aren't clear to you yet, when we do our in-class exercise, I hope that we'll be able to illustrate some of those a little bit better. So when your sinusoidal wave is flowing down a transmission line, it is sinusoidal in both time and space. The voltage and current move at the same velocity and remain in phase, and the characteristic impedance can be found according to the square root of L hat over C hat. The velocity of propagation along that line is c over the square root of epsilon r. We have shortcut versions of the equations for the characteristic impedance of each of the 3 types of transmission lines. When a transmission line is terminated in a load impedance, we'll get reflections, and the reflection coefficient can be found by z sub L minus z sub c over z sub L plus z sub c. For a short-circuited line, gamma is negative 1, and the viswar is infinity. For an open-circuited line, gamma is positive 1, and the viswar is still infinity. For an impedance matched line, there is no reflection coefficient, and that's a typo, and viswar is equal to 1. I'll correct that in your version. So the viswar is 1 is the best case scenario. The viswar is the ratio between the maximum voltage and the minimum voltage. It's 1 plus the absolute value of gamma over 1 minus the absolute value of gamma. Or you can modify that equation in case you know the viswar. There are actually tools that will tell you the viswar along a line. From that, you could calculate the reflection coefficient as viswar minus 1 over viswar plus 1.